I guess we can start now. Okay. Welcome to the Computer Security Seminar at Purdue University. Our speaker today is Jintai Ding from the University of Cincinnati, and he will speak on internal perturbation of multivariate public key cryptosystems. Jintai.
Thank you. First, I would like to thank the organizer, especially Sam, for the opportunity to give this lecture here. The title of the lecture is called Internal Perturbation of Multivariable Public Key Cryptosystems, and I'm from University of Cincinnati. This lecture basically contains two parts. First, I'll give an introduction of cryptosystems. In particular, I introduce what is a Matsumoto-Imai system and what is linearization equation attack and their generalizations and so on. And then I'll present the second part of the talk, which is about internal perturbation. So introduction. So what is a multivariable public key cryptosystem? I assume here everybody knows what is a public key cryptosystem. And the most famous one, of course, is RSA. But RSA is based on a number theory principles and is used as a function of one variables. And the multivariable public key cryptosystems are cryptosystems based on functions with multiple variables instead of single variables. And let me give you a quick example. Okay, so in this case, the cipher is given as a function with n variables and mapped to a space with m components. Okay, and this is each component gi here are multivariable nonlinear polynomials. Okay, this is the public key, and any plain text is given as an element of a vector, and such that if you want to encrypt, you just calculate the value of this vector using this map. And to decrypt the cipher text, you need to know some secret, which is basically the secret key, so that you can invert map to find the plain text. And then first, I want to present a toy example. So we'll use a finite field K, and this is a degree 2 extension over Z2. And then in this case, we have 4 elements. We'll denote these 4 elements just by 0, 1, 2, 3. Here, 0 represents 0, of course, and 1 represents 1. 2, however, stands for x, and 3 stands for 1 plus x. This is an example of a finite field. And one of the examples is given by the following. You have G0 with 3 variables, and G1, G2 as well, and they are quadratic polynomials. Okay? So suppose you have a message which x0 equal to 1, x1 equal to 2, and x2 equal to 3, which are elements of the finite field. You just calculate the value. You can see the cipher text is going to be y0 equal to 1, y1 equal to 0, and y2 equal to 1. So basically, you have a message, and then you just put the message into the function and calculate the value. Okay? And this is a bijective map, which means we can invert it. And this is an example which we produce based on Matsumoto-Imai cryptosystem, which I'll explain later. Okay? What is the theoretical foundation in terms of security for such an idea? Okay? And it is the proven theorem which says that if you have randomly chosen n variable, n quadratic functions, quadratic equations, if you want to solve it, this problem in general is an NP hard problem. Okay? And why this is a foundation? Because when you attack the system, what you need to do is solve a set of quadratic equations. So if you can solve a set of quadratic easily, you can break all the systems. But we know, because it is NP hard, therefore we know it is very difficult to what? To break it using such a principle. Sorry. Okay? And another thing here I want to emphasize, if you notice that the functions we want to use in general are quadratic functions. Why so? Because you can see the public map are given by polynomials. And if you have a polynomial with n variable, if the degree high, the public key size will be too large. So in order to do things efficiently, you must what? make the degree as low as possible. Of course, you don't want to choose linear because linear equation can be solved easily. Okay? So therefore, you always want to build a quadratic system. Okay? And from mathematical point of view, also it makes sense because we know if you want to solve a polynomial equation, the degree high case is no different from degree lower case because we know every high degree polynomials can be reduced, polynomial equations can be reduced to quadratic equations by adding more variables. Okay? Therefore, we always like to do quadratic maps. Okay? And the fundamental motivation to build such a system coming from two. The first one, of course, is to resist the quantum computer attack. So by now we know all the number theory-based problems can be what? Can be broken. A number theory-based crypto system can be broken easily if we have a quantum computer. And by this stage, we do not know, or we cannot show that quantum computer can help at this moment. Okay? And the second motivation is efficiency. We know RSA system at this stage, minimum requirement if you want to have a secure system is 1,000 bits. In this case, the computation is very large. That means we cannot use existing public crypto system for small devices, for example, RFID tags or sensor networks. So people are looking for things which are much more efficient. And in this case, if you use small finite fields, it seems to us that there's a great potential we can build a system which are much faster than RSA. Okay? So those are the motivations. And I want to give a short introduction of the history of the multivariable cryptosystems. The idea of multivariable cryptosystems first was suggested by Diffie and Fair. Okay? At the beginning of the 1980s. And even though they suggest the idea, but they could not realize it. And later, Shamir did some work. But Shamir's suggestion also did not work. It was broken very quickly. And the first substantial breakthrough was the system developed by two Japanese guys. Their names are Matsumoto and Imai. Okay? And then later, it was broken. But however, Pataran picked it up. And Pataran and his research group did a tremendous work to produce new systems. And here I want to also mention one example, which is TTM. And this is a system invented by Professor T.T. Moore here at Purdue, even though all of them are broken. And now I also want to mention S-Flash. Okay? So last year in Europe, they take S-Flash, which is a Matsumoto Imai minor system. They accept it as a security standard for low-cost smart cards. And this is called a NISE program. It's a new European security standard. Okay? And this example is a multivariable crypto system. And the name is also S-Flash. And you can see the motivation for this here is for low-cost smart cards, which means for small devices. And they are very fast. And now I want to give a quick introduction about Matsumoto Imai system. Okay? And let's first fix a notation. So I have a small finite field K, and which is characteristic 2, and the size of the field is Q. And then I do algebraic extension of this field, a degree n algebraic extension of this field, and I have a bigger field called K bar. Okay? And of course, we know K bar can be identified with the n-dimensional K linear space, and I define this map phi and the phi inverse, which can transform back and forth. Okay? And their idea is very simple. Okay? And this idea was proposed in 1988. And they proposed to use this map F, which is defined over the bigger field K bar. You map an element in the bigger field K bar to x to the q to the theta plus 1. Okay? The important thing of this is quadratic property. And so this is a map from big field K bar to K bar. And then we can compose phi and the phi inverse on both sides. Now it becomes a map from K to the N to the K to the N. And this map is quadratic. And you would ask me why it's quadratic? Because you notice that x to the q to the theta plus 1, of course, is equal to x to the q to the theta times x. This is a linear map. If you look at it in terms of smaller field, and this one is also a linear map. This is what we call the Frobenius map. Okay? So you have two linear maps. You